Hi, I'm Krishna, and this is day 3 of 30 Days of Understanding Modern AI Stack. So, in this video, we're talking about activation functions, one of the core ingredients that gives neural networks their power. Imagine neurons in your brain. When a signal arrives, they decide whether to fire or not. And artificial neurons do something similar. They take weighted sum of inputs, Wx plus b, and then decide what to output. The way they decide is through an activation function. In simple terms, an activation function helps the network decide what information is important and what is not. If we did not add any activation function after a linear layer, Wx plus b, then deep networks would just collapse into one single linear transformation. No matter how many layers you stack, they could not learn anything complex. That's because linear functions only give you straight lines or flat transformations, and combining them just gives another straight transformation. Activation functions break this linearity. They bend the path so the network can approximate curves, patterns, and complex mappings. Without them, neural networks would be nothing more than linear regression stacked on top of itself. Early on, people use sigmoid and tanh functions. Sigmoid squashes values between 0 and 1, useful for probabilities. Tanh function squashes between -1 and 1 and is zero centered, which helps with training stability a bit. But both have a major problem. They saturate. For inputs far from 0, their gradients become very small. This slows learning deep networks drastically. Then came ReLU, Rectified Linear Unit, one of the biggest breakthroughs in deep learning. ReLU simply says ReLU of x is equal to max of 0, x. If input is negative, output is 0. If positive, output is the same. Even though it looks simple, ReLU is non-linear and lets gradient flow for positive values. This avoids much of the vanishing gradient problem and trains very quickly. But ReLU has a downside. If a neuron gets only negative input, its gradient becomes 0 and it can die. So some neurons never learn. To fix this dead ReLU's problem, people invented things like leaky ReLU, where instead of 0 for negative values, we let a small slope. See, this keeps gradients alive even on negative inputs. Variants like parametric ReLU and ILU also try to fix similar issues. As research progressed, smoother activation functions came along that keep gradients flowing everywhere. One example is swish, which is x into sigmoid of x, which is smooth on both sides and captures patterns better than plain ReLU in some tasks. Another is GALU, Gaussian error linear unit, used in big models like BERT and GPT families. Unlike hard cutoff and ReLU, GALU gives a smooth activation that works really well for deep language models. In classification problems with multiple classes, we use softmax at the end, and it is only for the output layer. It turns raw scores into probabilities that sum to 1, perfect for picking the most likely class. Activation functions are the gatekeepers of nonlinear learning. Without them, no curves, no learning, no patterns, no intelligence. With them, networks can represent anything. This is the heart of deep learning. Here's a quick list of the activation functions we have talked about in this video. And this list isn't exhaustive, but these are the ones you will see the most in real models. So that's activation functions, the tiny mathematical gates that turn simple linear operations into something powerful enough to understand real world tasks. Tomorrow we'll build on this and start exploring how models understand word meaning, embeddings, and vectors. See you then in the next video. Let's do it.